physics time. Tic-tac physics. Look. Say it.
Tic-tac physics time.
Tic-tac physics time. We got the tic-tac lights. We're going to try it with the... I'm going to take my mask off so anyone can understand me. We're going to try it with the tic-tac lights and see how it works. I'm going to have to write a little bit bigger. This is more ambient. It adds some nice atmosphere to it. Physics should be pink, I think. We're talking about...
I would say physics is blue.
I think you're probably right. Newton's second law. But the blue light, you know, people, you're going to stay up all night if we turn this blue light on. That's what they say anyway. People got them glasses. People got, since glasses are, since I have glasses, and that's why this is, but glasses are stylish because I have them. And so people who don't even need glasses wear them now with the excuse that, oh, they're blue light filtering. You've heard people say that. Yeah. And they look cool, because they are cool, because glasses are cool. But anyway, the excuse is that the blue light somehow makes it so you can never sleep again in your entire life if you look at it. So we're going to keep it on pink. Newton's second law, which actually has some blue in it, whatever. Newton's second law is what we're talking about today. Tell me in words, as a description, tell me Newton's second law.
That's a tough question.
We could write it as Newton wrote it, which was in Latin. And we could quote exactly what he said, but I don't speak Latin that well, and I don't remember exactly what he says. But give me a basic rundown of Newton's second law in words.
The acceleration the net force causes, okay,
that's pretty much the whole thing. But go on.
Is directly proportional to the magnitude of the net force in the same direction.
Yes. Let's simplify it.
Inversely proportional to the mass.
Yep. Acceleration
as acceleration goes
is directly dependent, directly proportional to net force and in the same direction. A corollary, or a side note, and I use that word too much. Another true thing about it that's related to this, corollary is fine, is that it's inversely proportional to mass. Acceleration is directly proportional to net force and in the same direction. And how is it related to mass?
Inversely proportional.
Inversely proportional and in the opposite direction? No, that doesn't mean anything because mass doesn't have direction. Maybe if mass did have direction, it would be, but it's inversely proportional to the magnitude of the mass. Effectively, bigger force, big F, bigger force equals what?
Bigger force equals bigger acceleration.
Bigger acceleration for a given mass. F equals ma. What if mass gets bigger here? What must happen? If the force stays the same and the mass gets bigger, the acceleration decreases. What if we needed acceleration to stay the same but the mass got bigger? We'd have to impart a larger force, right? Me and the student council, when we set up for the homecoming dance, me and the student council on Saturday morning went to the DG to get some decorations. Usually in my car I haul these things. Me, my wife, the dog, and the baby. And the student council has more mass, the whole thing has more mass than my wife and my child and my dog. And so my car handled differently. I know it's with greater mass to get the same acceleration to both negative accelerate when I was stopping at a stop sign or to positive accelerate when I was going faster. It took more force from my car. I had to gun it a little harder, right? I had to give it a little bit more force to overcome the mass. This is true, but it kind of almost, even though this is similar to the way Newton would have phrased it in Latin, it kind of misses the point. The point of Newton's second law is that net force causes acceleration. They are not just related. They are related. They're directly proportional. But net force causes acceleration. What does this imply in the other direction? Net force causes acceleration, but that must mean that every acceleration, what?
It has a net force.
Is caused by a net force. Every net force causes an acceleration, and every acceleration is caused by a net force. This relates to my favorite picture. Remember my favorite picture? How does it relate to my favorite picture?
Wasn't it the dude on the boulder?
Yeah. The guy who, oh, because the boulder moved without, because that was demonstrating inertia. But it also demonstrates this.
Wait, Net force causes acceleration, but if there's no net force, it wouldn't cause acceleration.
Yeah, there's no acceleration.
Got it.
Remind yourself, what are the two ways, remind me too and remind the camera, what are the two ways an object is not accelerating?
Moving at a constant speed in a straight line.
Good, we got the hard one pegged
Or at
down.
rest.
Yeah, rest, that's easy. Or straight line, constant speed. If we see an object at rest, like a boulder, what must be true of it?
There's no net force.
No net force. No force is acting on it?
No.
Not necessarily. No net force. Here's the boulder. It's shaped like a boulder. Kind of like a sock and a kidney had a baby and made a boulder. Anyway, what are the forces acting on it? Could there be no forces? Like
No.
theoretically, in the universe, could there ever be no forces acting?
No.
Technically not, but we could effectively negate gravity because it's so minuscule. If there were no forces acting on it at all, would it accelerate?
No.
No,
It just-
no net force would mean it's doing one of these
It
things,
would
right?
fall apart.
Cute. Okay, true, but we're not talking about that right now. But even we're sitting on Earth, which we assume the boulder is when it's standing next to the guy going, "Ah!"
Cute.
I mean, how do you make him look concerned? There we go.
Yeah. Now he just looks like he has weird hair.
Well,
Those
he
are-
doesn't. Those are his eyebrows. Okay, no net force. It's on Earth. No net force does not mean there's no
It's on
forces. What
Earth.
forces are acting on him?
Gravity.
Or on him, on the
and
rock.
The normal force.
Yeah, the force of gravity, which we also call,
Weight.
and the normal force. And they must be the same because the net force equals,
Zero.
0, and therefore it does not accelerate.
Still.
No acceleration. Okay, well, what's another case where an object could be not accelerating we just talked about?
When you're driving on the
Yeah, you're
interstate
constant
and you
speed.
got your cruise set.
Let's do that one. Let's do that one. What are we driving here?
A Subaru Outback.
Okay.
That's what my mom drives.
Yeah, that's a nice car. It's an alright car. This is pretty much a Subaru Outback.
Pretty much.
Gotta have the Pleiades on
And you
there.
gotta get your luggage rack on top.
Oh yeah, heck yeah, that's what makes it look like.
There we go.
There we go. Okay, we're driving our Subaru Outback with a bottle nose apparently. Make it a little bit more like a 90s Subaru Outback, which is the good years of the Outback. Anyway, we got the Subaru Outback. Accelerating? Let's say it's not because, as Levi says, it's going down the interstate in a straight line at a constant speed. The cruise is set. It's your mom. How fast does she drive on the interstate, would you reckon?
90.
85 probably.
85. Great. Okay, doesn't really matter though. Let's do so what we already know, if it's not accelerating, which it's not, it's moving in a straight line at a constant speed. Moving in a straight line at a constant speed. So what must the forces acting on it be like?
Equal.
They must be balanced, okay? So let's name some. What's one force acting on it?
Gravity.
The normal
F
force.
sub G, its weight, the normal force, which must exactly counteract gravity. We're going to assume it's not on a hill. It becomes more complicated if it's on a hill. Good, okay, which way is friction acting?
Backwards.
Yeah, to the rear, right? We're going to say it's quite a bit larger
F
than...
sub F.
Yeah, F sub lowercase f.
But then you have the force of your.
The force of the
Motor.
engine.
Yeah, we'll call this,
the workforce.
what it actually is friction. It's the friction on the tires going the other direction, but we'll call it the force of work. Sure, that's fine. Probably actually not greater than its weight. I don't know, it's kind of hard to tell. But the forces are balanced. There are X forces. Unlike the boulder, there are X forces. Don't take this to mean that if there are X forces that it's doing this one, and that if there aren't, it's doing this one. That's definitely not always the case. But all the forces must be balanced in both X and Y. What's another very common way that an object can be doing the second one, straight line, constant speed, without accelerating? Your book talks about it. I don't know if you've read your book. I hope you have.
I'm not sure what you're referring to.
What's another very common way an object can be that is not accelerating, but it is moving in a straight line at a constant speed? When it is doing what? Falling. When it's specifically when it's falling at terminal velocity. So we're going to write terminal velocity. We went into great depth about the origins of the meaning behind the phrase terminal velocity on the video I just did this morning for the freshmen about Newton's second law, or Newton's, yeah, that's right. Actually, it would have been last week that we did the video. I talked about it in the Bell Work today. Anyway, well, what kind of object is falling here?
Plane out of the sky. on
Yeah.
fire.
Well, okay, plane
A
makes it
plane
difficult because
falls
the
on
plane's
the border
blind.
of U.S. and Canada
Okay, yeah. Where do you bury the survivors? No, let's pick a different
shark.
object.
because the shark's up there.
Okay, a shark.
It says Sharknado, dog.
Sharknado.
Yeah, Sharknado, there we go.
Not gonna lie, that was low-key was a good movie.
No, it wasn't, but it was good because it wasn't good. Okay, there's a shark. It's seen better days. It looks like it's already been buried in Iceland for 3 years, being made
It's a
into stone
Greenland,
strong or
it's a
whatever they call it.
Greenland shark, dude. Those bad
There
boys
we
that
go.
live like
Okay. So if it's falling at terminal velocity, what this means is that it has no acceleration. Is it moving?
Yes.
Yes, it's still moving. Things when they're at terminal velocity don't just hang midair, stop falling altogether. It just means that they're moving down a straight line, specifically down at a constant speed. And that constant speed is their terminal velocity. So in the same way as our rock that was just sitting there, it still has two forces acting on it. Weight, but in this case, instead of the normal force, it is
Air resistance.
air resistance, which we also call drag, F sub D, which is drag. And when those perfectly balance,
You sit there.
yeah, what, do you remember, Ty, just, this is from your lab, why I asked you specifically, what are the things on which drag depends?
The surface area. Or the
Yeah,
surface
the
constant.
cross-sectional area presented towards
Yeah.
the
Oh,
fluid.
the drag coefficient. That's
The
what
drag
it is.
coefficient, which is some other, it's a constant, but yeah, the drag coefficient, which does vary from object to object, but it doesn't change for one specific object.
Density.
The density of the fluid,
Yeah. Velocity.
velocity, that's the key one I was getting at. So the greater this velocity of this falling shark gets, the stronger the drag force gets. So when it first started out, there would have been probably very little drag because it weighs quite a lot, for one thing, and its cross-sectional area is probably not great. Its drag coefficient, actually a shark is designed to have a low drag coefficient so it can go through the water, which is a fluid, much more easily. Anyway, so all those things are quite small, but the faster it gets, the velocity increases, right? And the velocity increases the drag little by little by little until eventually the drag force is exactly equal to the weight, and from that point on, the object stops falling.
No, it just goes
No,
down. at
exactly.
constant speed.
It doesn't stop falling. It doesn't stop moving, but it stops accelerating. It begins falling at a constant speed instead of at an ever increasing speed. Is gravity still acting on it?
Yes.
Yeah. Is it still accelerating at 9.8 meters per second squared?
Yes.
No.
No.
What's it accelerating at?
0.
0. There's no acceleration. So, does gravity always cause objects to fall at 9.8 meters per second squared?
No.
Not if there is
Equilibrium.
not if there's any fluid resistance at all.
Yeah.
Not if there's any fluid resistance at all. In fact, it goes down even for an object like this. I'm not going to draw because we'll ruin the floor. But even for an object like this, will eventually slow down. And it'll even measurably slow down if we drop it from a high enough place on Earth's surface, okay? That's one of the reasons why in physics, especially at the beginning when we were doing
Well, wait.
linear motion, why we negate air resistance, because it does complicate things. But now that we're talking about it, it's not that
So it
complicated.
slows down, but then when it speed up again, it wouldn't. So
It'll just this would have a fairly high terminal velocity.
It would just
because
continue?
It has very low surface area, very low drag coefficient because it's smooth. It's quite weighty. It would take a lot of drag. In fact, this thing probably would get going very, very quickly if we dropped it.
so wait. So you said that it would slow down. So
Yeah. No, not slow down. It's acceleration would decrease. I may have said slow down, but I'm glad you pointed that out. What would actually happen is the acceleration would decrease. It'd be the acceleration approaches 0 the faster this goes because the drag increases.
got it.
The title of this that I was trying to get you to talk about is Free Fall Explained. In Chapter 1, we had a section called Free Fall.
Yeah.
In Chapter 2, we had a section called Free Fall. Chapter 3, we had a section called Free Fall Revisited, which is where we talked about, instead of the distance and time, we talked about acceleration. And now this one says Free Fall Explained. We're telling the reason why free fall exists, which is this, the forces behind it.
Solid.
Okay? Your book does talk about, for maybe about a third of the chapter is friction, but it's enough for you to know that friction exists because of what?
Because of things
Well,
affecting
good.
motion.
No,
Two
friction.
things rub a dub on each other.
Yeah, rubber. Friction is a contact force. It only happens when they're in contact, and it resists
Motion.
motion. Actually, let's not put that because that's the same terminology we use for inertia. I'm going to say it opposes motion, or what I call intended motion, not just other people call it that too. Motion or intended motion. I mean intended motion by if I have the Promethean board over here. If I push it, which I'm pushing it fairly lightly, but I'm pushing it. What's stopping it from rolling?
The
Friction.
Friction. Yeah, the brakes are on. In fact, that's why the brakes are on, because there's a kind of friction called rolling friction, which is what the tires have, which is for the same frictional coefficient, which we're going to talk about in a second, and the same normal force. Rolling friction is significantly less than sliding friction. And so that's why things have wheels, and that's why the brakes are set on this, is so the wheels can't turn. Basically, and we'll talk more about this in a second, or we'll talk more about friction in general in a second, but basically, rolling friction makes it so a different part of the object is presented to the other surface at every given second, and so it's always kind of a smaller amount of friction than sliding friction. Anyway, I have the brakes set. Friction is stopping this from being, so is it moving? No, so is friction opposing motion? No, it's opposing intended motion, where it would move if there wasn't friction. How can I make it move?
Take the brake.
I could take the brakes off, which would change it from sliding friction to rolling friction. And as I say, rolling friction is almost always, as far as I know, is always less than sliding friction
You
for the
can
same
put more
object.
force on it.
I could put more force on it, overcome the friction. What else could I do? That would actually be the one I would
You
actually
could
do if I
put
was
it
going to do it.
on something to change the surface.
Yes,
You
I
can
could.
turn off
What
gravity.
would be a surface that would... Oh, let's come back to that. But what would be a surface that would reduce the friction?
A dog.
That's not a
if we were
surface.
to wet the floor.
Yes, okay, we could lubricate it, which reduces friction. That's what lubricant does. Or we could change the surface altogether. If
Yeah.
it was on ice instead of
Yeah.
hardwood, how could we increase the friction? What could we put it on to make the friction more?
Sandpaper.
Gravel, sandpaper. I think when you do football practice, you have like a little jump up platform where you like do it to jump onto an angled surface, and that's covered in basically sandpaper to increase the friction so you don't like slide off and break your neck. Right. Anyway, you said something about we could turn off gravity, but it's actually not gravity causing the friction. What it is this is the formula for friction. So write this down, please. It's fairly simple, but F sub lowercase f, the force of friction, equals the normal force times what we call the coefficient of friction, mu. So F sub f is friction force. What unit do you reckon we measure that in?
Newtons.
Yep, you're right. F sub n is the
Force.
normal force. Thus far, we've talked about the normal force as directly opposing gravity.
Yeah.
But you should know this. The normal force always acts perpendicular to a surface. Which way does gravity always act?
Down.
Down. So check this out. Here's my podium of science. Yeah?
Yeah.
Okay, stay up, podium of science. Which way is friction acting right now? Which way is gravity acting right now?
Down.
Down. Directly down. Which way is the normal force acting?
Up.
Directly up. The object here is my book. Okay? If I tilt this, which way is friction acting? Which way is gravity acting?
Straight down.
Still straight down. Which way is the normal force acting there?
Straight up.
No.
Oh,
It's
yeah.
perpendicular. So now the normal force is acting this way. So what is holding the book there? There has to be another component, right? There has to be another component that stops. Look, if I turn it just a little, now the normal force is acting not quite at a 90-degree angle, right? Gravity's acting down.
Well, it's friction, but it's also
It is
flat.
friction. It's this. It's friction with the platform. So if I have, when it's straight down and up, here's the book. Gravity acts down. I keep doing that wrong. Gravity acts down, the normal force is straight up. When it's turned a little, now the normal force is acting still perpendicular to the surface. It has to. Always perpendicular. So what makes up the difference?
Friction.
Friction. The force of friction. And you can see if we break those components up, they add together to make the same as gravity. What if I turn it more and more? What's happening eventually as I turn it more and more?
There's more friction.
No?
There
There does have to be, but to a point.
Affected.
Eventually,
More.
there it went.
The book moves.
The book moves
At a certain
because...
point, there's not enough friction.
Right. How can I make it so my book doesn't slide off later?
You could put like something that's more.
Scratch at the cover.
Yep. Yeah, I could make this less smooth. So, and then the last thing that relates to that is mu, which is the friction coefficient, which has no units. And this depends entirely on the smoothness of the surfaces. Lower for smoother, higher for less smooth. You can look up, there are tables upon tables upon tables online of like rubber on concrete. It'll have one object and another object, or sorry, one surface and another surface, and it'll tell you the coefficient of friction. Some good tables will even say, here's the coefficient of static friction, which is what's holding it there, if it were just still, coefficient of sliding friction, which is less, and coefficient of rolling friction, which is even less. But mu is the friction coefficient, which is unitless. Figure 5.5 in your book is lovely. I love it. Open your books to page 63 and look at figure 5.5. It says, there are two kinds of dividers here. It calls them dividers. I would call them guardrails. You know about guardrails on the highway. Yeah. You can actually see both of these types right now. If you look out the window, I can't turn the camera, but if you look, see the bridge?
Yeah.
On the bridge itself is the one kind we're going to talk about, and right before the bridge is the other kind. Let's read it. It says, cross-sectional view of concrete road divider and steel road divider. Which design is best for slowing an out-of-control side-swiping car? Okay, so we have two kinds. We've got the kind that is like a wood post with a steel girder run along, and we have the kind that is concrete, which is fatter at the bottom than it is on the top. Assuming that the normal force is going to be the same between them, what about this is the only thing that's going to be different?
The mass.
No? Well, probably not.
I mean the angle, right?
Probably not. Maybe, but probably not. The one thing about this equation is going to be different.
Okay.
We're assuming it's pressing in with the same amount of force.
The friction coefficient.
The coefficient of friction. Yeah, so it's going to be either metal girder on what part of the car is that going to touch?
The door.
Probably the metal part of the car. So metal girder on metal car, or the fatter at the bottom concrete is going to be what?
On the tire.
Yeah, concrete on rubber. Mm-hmm. So there's going to be a greater coefficient of friction. So why have both? What's the trade-off? Why not just have? We just said the concrete is going to be.
Concrete is going to send you flying over the bridge.
Well, the concrete is probably going to stop you better. Isn't that what we agreed?
Uh-huh.
Yeah.
So if you look at the bridge itself has concrete girders.
Okay.
Why didn't they just use that the whole way? Why are there still girders at all behind it?
Because it's not that big of.
Yeah. Okay. That's exactly. There's a cost benefit
It's not that big
analysis.
of cost. Like if you go off the middle one.
The steel one is cheaper.
Yeah.
And if you blow through that right there, you'll be in someone's lawn. It'll suck, but you'll probably live. This concrete one's more expensive, but if you go through, if they use steel girder there and you went through it, you'd be on the railroad tracks. First of all, it's a 50-foot drop. Your car would probably be crunched, and so would you. And there might be a train coming, and you would certainly die if there was a train
Or you
coming.
fall in a cold car and just go to Wyoming.
Or you just go to Wyoming on a cold
Which
truck.
is worse than that.
So they did the cost-benefit analysis. They decided, you know what, we should use, if it was a perfect world, concrete were unlimited, we'd use concrete for every road divider.
But no.
Because it's better. But it's cheaper to use the wood and metal.
Our government doesn't like... Our government's stingy.
Yeah, but it also doesn't really matter that much. So. Okay. On your test, you'll be expected to be able to calculate friction. You'll be expected to use F equals ma. You'll be expected to explain terminal velocity. You should remember Newton's second law and how that relates to all of this. Do you have questions about any of this?
No, goodbye.
So the stuff from the previous chapter about... there also is... Your book does talk about pressure. I'll trust that you do that on the chapter review. But you don't have questions about any of this?
Nope.
Bye! Okay.